Welcome everybody once again. So we are in our third module and this is our 15th class. In the last class, in the previous class, we saw one problem on hydraulic gradient line and total energy line. We will continue that. Today we are going to see two more problems. We will try to solve two more problems. So the first problem is a horizontal pipeline 40-meter long is connected to a water tank at one end and discharges freely into the atmosphere at the other end. So we have a tank. Okay, we have a water tank and a horizontal pipeline of 40-meter long which is attached to the tank, which is connected to the tank at one end and it discharges freely into the atmosphere. So we shall draw a tank. And it is given the pipeline is horizontal. So this horizontal pipeline is 40-meter long. Okay. So we know the flowing liquid is water, right? Water is the flowing liquid. Now, for the first 25 meter of its length from the tank, the pipe is 15 centimeter diameter and its diameter suddenly enlarged to 30 centimeter. Okay. So for first 25 meter of its length from the tank, the pipe is 15 centimeter diameter and then it is doubled to 30 centimeter. So that means, so we shall take up to here. Okay. Up to this point it can be 25. And after that the size of the pipe is doubled. So this is 25 meter. The first pipe is of length 25 meter and the second pipe is of length 15 meter. So that totally we get 40 meter. Also the diameter of the first pipe, let us take this as D1 and A1, area of the pipe is A1 and the diameter of the pipe 2 as D2 and A2 respectively. Now, let us write the given data. So, the given data are the length of the pipe L is equal to 40 meter, L1 is equal to 25 meter, L2 is equal to 15 meter. For the pipe 1, D1 is equal to 15 centimeter diameter, that is equal to 0.15 meter. And D2, diameter of the second pipe D2 is, it is doubled, it is 30 centimeter. 30 centimeter, so it is 0.30 meter. Okay, now the height of water level in the tank is 8 meter above the center line of the pipe. (8 meter above the center line of the pipe. So the water is up to a level of 8 meter, right? This is the free surface of water. Water is flowing out. Okay. Now, considering all losses of head which occur, determine the rate of flow. So, we need to find what is Q. We need to find what is the rate of flow of the water. Now, it is given as take the coefficient of friction F is equal to 0.01 for both sections of the pipe. So, both the sections of the pipe, there is coefficient of a friction. So, if there is coefficient of a friction, that means there is major loss. Friction, that is losses due to friction is major losses. So, we know the formula for friction is FLV, losses due to friction will be equal to FLV square, 4FLV square by 2GD. So, this loss, this major loss, it depends on the coefficient of a friction, the length of the pipe, velocity of the pipe and the diameter of the pipe. So, the head loss due to friction differs in pipe 1 and pipe 2. But the coefficient of friction is remaining the same. That means we have to find the loss of a friction due to pipe 1 and due to pipe 2. Now, we need to find the hydraulic gradient line and total energy line. So, three things we have to determine. Hydraulic gradient line, total energy line. So, three things is asked in the question. The rate of flow, hydraulic gradient, we have to draw the hydraulic gradient line and the total energy line. So, how will we solve this problem? Now, okay, now the height of the water, H is given as 8 meter, right? H is equal to 8 meter. Okay, the given datas are over. Now we will apply the Bernoulli's equation to the free surface of water in the tank and outlet of the pipe. Now, let us take the reference line or the datum line along the center of the pipe. So, this is the center line of the pipe. So, let us take this as the datum line. Okay. So, this is the datum line. So, we are considering a datum line along the center line of the pipe. Now, let us apply the Bernoulli's equation. So, let us take section 1 on. Let us take the section 1 on the free surface of water and section 2 at the exit of the pipe. So, this is taken as section 2, point 2 or section 2 at the exit of the pipe. So, 1 is taken at the free surface of water, 2 at the exit of the pipe. Now, apply Bernoulli's equation. So, we are applying Bernoulli's equation to the free surface of water, that is for section 1 and outlet of pipe, that is our point 2 or section 2. So, when we apply the Bernoulli's equation at point 1 and 2, we know the Bernoulli's equation is P by rho G, so P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2 plus all losses. So, what are the losses here? All losses means it is due to friction. So, we have the frictional loss in pipe 1, frictional loss in pipe 2. They are the major losses. Now, we have the minor losses. So, minor losses at the inlet of the pipe 1 Then here we have another loss, that is in the exit of pipe 1. So we have losses in the entrance of the in the inlet of pipe 1, in the outlet of pipe 2. Since we are considering the outlet in pipe 1, see here there is inlet in pipe 1 as well as exit in pipe 2. Only one should be considered. Either consider inlet of pipe 1 or consider exit, either consider, see here there is exit in pipe 1 and inlet in pipe 2. So either consider exit in pipe 1 or consider inlet in pipe 2. So we will consider exit in pipe 1. Okay, we are not considering inlet, we are considering exit in pipe 1. So the major losses are losses due to friction in pipe 1, losses due to friction in pipe 2. The minor losses are here losses due to inlet in pipe 1 and losses due to exit in pipe 1. Okay. Now, so in the free surface, we know pressure head P1 by rho g will be equal to 0 plus the velocity head on the free surface of water will be equal to 0 plus Z1. So this is our datum line. So Z1 is 8 meter. 8 is equal to P2 by rho g. So at the free, here also, listen, at point 2, it is also free to atmosphere. So your pressure head, pressure intensity will be equal to 0 at point 2 because it is free to atmosphere. So 0 plus, there is a velocity, right? There is a velocity. So we will consider V1 as the velocity in pipe 1 and V2 as the velocity in pipe 2. So we have V2 square by 2G plus Z2 lies on the datum line. So it is a 0 plus all the losses. We have frictional loss in pipe 1 plus frictional loss in pipe 2. These are the major losses plus HI, that is minor loss due to the inlet of the pipe and minor loss due to the exit of the pipe. HI is minor loss due to the inlet, and here see there is an exit as well as sudden enlargement. So when you are considering exit and sudden enlargement, the losses due to sudden enlargement will be greater. So here we will consider enlargement. Okay, so here E means enlargement of pipe. Okay, enlargement of pipe. See, I told you it is an exit, but in this case it is enlargement of pipe. Okay, enlargement of pipe. Now, so what is HI? We will find what is HF1, what is HF2, what is HI and HE. Then we will substitute in this formula. Okay. So from this we get 8 is equal to V2 square by 2G plus HF1. Now what is HF1? HF1 is 4FL1 V1 square by 2GD1. plus HF2 is 4F L2 V2 square by 2G D2 plus HI, that is loss of head at entrance or inlet, is equal to 0.5 V1 square by 2G. Okay, at this point, inlet of pipe 1, 0.5 V1 square by 2G, and HE, that is the loss of head due to sudden enlargement, is, we know, V1 minus V2 the whole square by 2G. Now, G is 9.81. We know L1 F D1. We know L2 F D2. So here there are two variables, two unknown variables, V1 and V2. So we will write either V1 in terms of V2 or V2 in terms of V1. So it is better to write either, it's our choice. You can write V1 in terms of V2 or V2 in terms of V1. So what we get is, see, for obtaining V1 in terms of V2 or V2 in terms of V1, we have to apply the continuity equation. So we will give this equation as 1. Now we will apply the continuity equation. So we know continuity equation is Q is equal to A1 V1 is equal to A2 V2. Writing V1 in terms of V2, we get V1 is equal to A2 V2 by A1. Now we know V1 is equal to A2 is pi D2 square by 4 into V2 by pi D1 square by 4. So we know D2 is 2 times of D1, right? 2 times of D1 the whole square into V2 by D1. So we get 4 D1 into, so here also we have square, right? So it is 4 V2. So from which we get V1 is equal to 4 V2. Okay, now we will substitute V1 is equal to 4 V2 in equation 1. So we get 8 is equal to V2 square by 2G. So 2 into 9.81 plus 4 into F is given as 0.01. 0.01 into L1 is 25 meter, pipe length of the pipe 1 is 25 meter, V1 square. So V1 is 4 V2. 4 V2 the whole square divided by 2 into 9.81 into D1. Diameter of pipe 1 is 15 centimeter, right? So it is 0.15 meter. So 0.15 plus 4 into 0.01 into L2 is 15 meter, that is length of pipe 2 into V2 square divided by 2 into 9.81 into D2 is 30 centimeter, so it is 0.3 meter diameter of pipe 2 plus 0.5 into V1 square. V1 is 4 times V2 the whole square divided by 2 into 9.81 plus V1 minus V2. So V1 is 4 V2 minus V2 the whole square divided by 2 into 9.81. So here the only unknown is V2, from which we get V2 is equal to 1.113 meter per second. And for exam point of view, see, for exam point of view, there will be marks for your steps also. That means, see, sometimes even if we make some mistakes, the in between steps, if you are writing correctly, you will get the answer. So you can find all the values separately. See, for exam point of view, you can find the values separately. That is, you can find HF1 separately. You will get the answer as HF1 will be equal to 106.67 V2 square by 2G. You will get HF2 will be equal to 2 V2 square by 2G. HI will be equal to 8 V2 square by 2G, and HE will be equal to 9 V2 square by 2G. And this is just for exam point of view. Okay, if you find these things separately, even if you do some mistake in this calculation, you will get the marks for these steps. Here I have substituted everything together. Okay, you try to find HF1 separately, HF2 separately, HI separately, HE separately, then substitute. Okay, so that will be easy for you. Easy for you for exam point of view, that's all. Now, once we find V2, now we can find what is the discharge. So, discharge Q will be equal to, it is either A1 V1 or A2 V2. So, we will use A2 V2. So, Q is equal to A2 V2. So, that is pi into D2 square by 4 into V2. We get Q is equal to pi into D2 is 30 centimeter. So, 0.3 square diameter of the pipe 2 is 30 centimeter. So, it is 0.3 square by 4 into V2 is 1.113. We get Q is equal to 0.07867 meter cube per second. So, from which we can write Q is equal to, multiply it by 1000 in order to get liters per second. So, 78.67 liters per second. Because 1 meter cube is equal to 1000 liters. So, in order to convert meter cube to liters, you multiply it by 1000. Now, we will draw the hydraulic gradient line and total energy line. So, first of all, we will draw the total energy line, but then we will subtract the velocity head from the losses from the total energy line to get the hydraulic gradient line. Okay. Now, first of all, we will find the total energy line. We will draw the total energy line. Now, let us take a point A on the free surface of the water. Okay. So, at the free surface of water, first we will take at free surface of water, our total energy will be equal to P by rho G plus V square by 2G plus Z. So, we get at free surface of water, pressure head is 0, velocity head is 0, and Z is equal to, so at free surface, Z is equal to datum head is, this is our datum line, so datum head is 8 meter. Plus 8, so it is 8 meter. Okay, so there is no losses at the free surface of water. Now let us take the point at the inlet of pipe. At the inlet of pipe 1. So at the inlet of pipe 1, there is losses, right? There is losses. So total energy line will be equal to P by rho G plus V square by 2G plus Ez plus losses at the inlet of pipe 1. So now we are choosing this point, okay, at the inlet of pipe. So second, now we will consider, see, we know up to this there will not be any losses, right, at this point. Then at this point there is a loss due to the inlet of pipe, right? Loss due to the entrance of water or inlet of the pipe. So here there is a loss called HI, right? That is a minor loss. So in the second step, next case, we will consider second, at the inlet of pipe, at the inlet of first pipe, at the inlet of first pipe, the losses is HI, right? So HI is equal to, we know it is 0.5 V1 square by 2G. So we get 0.5 into V1 is 4 times V2, right? V1 is 4 times V2. So 4 times V2 the whole square by 2 into 9.81. So what we get is 0.5 into 4 times V2. The value for V2 is 1.113. So 1.113 the whole square by 2 into 9.81, we get 0.5 meter. So when we are drawing the total energy line, so remember this loss is 0.5 meter. So at A, that is at the free surface of water, at the free surface of water, the total energy is 8 meter. At the entrance, there is a losses of 0.5 meter. Okay. So at the entrance, there is a loss of 0.5 meter. So at the entrance, at this point, the total energy is 7.5 meter, right? So this distance is 0.5 meter. This is the loss. So we will take this point as A, this point as B. So you join AB. Now, see, that means the loss is 0.5. That means our total energy at the inlet of first pipe will be equal to 8 minus 0.5, that is 7.5 meter. That means from the datum line, the total energy at the entrance will be equal to 7.5 meter. So this is 7.5 meter. Okay. Now, okay. Now, See, from this point to this point, along the pipe L1, along the first pipe, there is a frictional loss, that is HF1. Okay, there is a frictional loss HF1. So from this point to this point, when the water reaches this point, we have the loss HF1. Okay, so now we will find what is HF1. We are finding at the exit of the first pipe. So third case, at the exit of first pipe. At the exit of first pipe, losses HF1 is equal to, we know, 4F1 L1 V1 square by 2 GD. So substitute the values. We get HF1 is equal to 6.73 meter. Okay. So losses is 6.73 meter. Total energy at exit of first pipe will be equal to, see, from this you have to subtract 6.73. So 7.5 minus 6.73. So we get 7.5 minus 6.73. We get 0.77, 0.77 meter. So from this you can subtract 6.73, or from the datum line you can take it as 0.77. From the datum line you can take 0.77, or it is from this line you subtract So here we will draw a horizontal line. See, from the datum line, the point A is 8 meter. Then we have point B. This point B is at a distance of 7.5 meter. Then you subtract, you get 7.5 minus 6.73. From the datum line, you get 0.77 meter. We can take that point as C. Okay, that point can be considered as C. So point C is at a distance of 0.77 meter. So from B you join a line to C. Now at C, at this point we have a sudden enlargement. So there is losses due to sudden enlargement. So now again at the exit of pipe 1, we have loss due to sudden enlargement. Loss HE is equal to V1 minus V2 the whole square by 2G. Substituting the value, we get HE is equal to 0.568 meter. So total energy at the exit of first pipe is equal to 0.77 minus 0.568 meter. We get as, let me subtract. So 0.77 minus 0.568. We get 0.202 meter. So here this is getting down to 0.202 meter. We will take that point as D. So we will draw a line from C to D. So the point D is from the datum line. This is at a distance of 0.202 meter. 0.202 meter. Okay, so from A to B, draw a line from B to C, then from C to D. Now, when you are coming here, when you reach at this point, there is a frictional loss in the pipe 2, that is HF2. So, find what is HF2. That is at the exit of pipe 2, right? So, now 5 at the exit of pipe 2. At the exit of pipe 2, we have the loss HF2. So HF2 is equal to 4F L2 V2 square by 2G D2. Substitute with the values we get. HF2 is equal to 0.126 meter. So total energy at the exit of pipe 2 will be equal to this 0.202 minus 0.126. So we get 0.202 minus 0.126. We get 0.076 meter. So here the total energy is from E, you can join a point E. So up to this, right? This is point E. So point E is 0.076 meter from the datum head. Join D, E. Now, this line, that is A, B, C, D, E. This line is called the total energy line. Total energy line, okay? That is line joining the total energy head. Line joining the total energy head from the free surface of water to the point of discharge of water. So A, B, C, D, E is called, the line A, B, C, D, E is called total energy line. See here, A, B, C, D, E, I have mentioned the total energy. Total energy at A, total energy at B. That is, total energy at A means at free surface, then total energy at the entrance of the pipe, then there is a loss. So up to here there will not be any loss. At this point there is a loss of 0.5 meter. Then from this point to this point there is a frictional loss. So it is a slanting line. So throughout this there is frictional loss. Then at this point there is a minor loss, that is due to sudden enlargement at this point. So there is a vertical line. Then from this to this there is a frictional loss. So slanting line. So this slanting line represents the frictional losses, or slanting line represents the major losses, and the vertical line represents the minor losses. Okay, you can mention it in other way also. That is, from A to B the distance is 0.5 meter. Now from B to C. Okay, what is the distance from B to C? You can mark it. Okay, you can mark the distance from B to C. So from B to C, what is the distance? Same way from C to D, what is the distance? Same way from D to E, what is the losses? You can mark that also in this diagram if you have space or if it is not congested. Now we will find the hydraulic gradient line. So we know hydraulic gradient line will be equal to, so total energy line is P by rho g plus V square by 2g plus Z. Whereas hydraulic gradient line is equal to pressure head plus datum head plus losses. That means we have to subtract this velocity head. We have to subtract the velocity head from the total energy head in order to get the hydraulic energy head. Okay. So next we will determine the hydraulic energy line. So for determining the hydraulic gradient line, so it is not energy, it is gradient. In order to obtain the hydraulic gradient line, from B, that is from this point, along this line, along this vertical line, see along this vertical line, there is a vertical line AB, right? So along this vertical line, we will subtract V1 square by 2g. Then the next line will be parallel to this line. Next in this vertical line, okay. So here see, from this B to C, from B to C and from D to E, okay, from B to C and from D to E. So for finding the hydraulic gradient line, from B we will take BG will be equal to, that is V1 square by 2g, that is 1 meter. Or else we will find the velocity head V1 square by 2g. So substitute the values, we will get V1 square by 2g as 1 meter. So subtract this 1 meter from this point B. Subtract 1 meter from this point B so that we will get this point. So this distance is 1 meter, that is the velocity head. We will take this point as, so up to E is over. So we will take this point as, let us take this point as G. Okay. So here, see, along this point, there is, we have to minus the velocity head. We have to subtract the velocity head. So we have to subtract V square by 2g. Now from this point to this point, draw a parallel line. Okay. Now, come to this point, that is at the exit of the pipe. When you come to the exit of the pipe, our hydraulic gradient line, see at this point, the hydraulic gradient line will coincide with the datum line. So we will take that point as F. Why this is coinciding with the datum line? The reason is, we know hydraulic gradient line is equal to pressure head plus datum head, pressure head plus datum head, right? So pressure head is equal to 0 at the atmosphere. Here the datum head is also equal to 0. That means at this point, hydraulic gradient line will be equal to 0. Now, from this point, you draw a line parallel to DE. So you will get, so this line, it is point, this is 0.076 from here, right? So you draw a line parallel to DE. Now join, see, take this point as H. So join these both and take this point as I. Now this is your hydraulic gradient line. So your hydraulic gradient line is GHIF. Okay. So this is how you need to draw the hydraulic gradient line. So how will you write this? So draw GH parallel to BC. Then from F, draw FI parallel to ED. Now you can join HI, which implies the line GHIF is hydraulic gradient line. And how is your total energy line? Is the line A, B, C, D, E is total energy line. Okay. So I think one problem is enough for today. We will see one more problem for this hydraulic gradient line and total energy line in the next class. Thank you.